All right, if you are not sitting up straight, go ahead and do that for me. Scooch forward. All right. I'm going to go ahead and let you know in advance. It's a lot of notes today. I'm sorry. Okay? It's a lot of notes, but it's a lot of important information. Okay? This entire unit is over what? Solutions. That's what this unit is called, is solutions. Okay? So this first portion is just a review of solution activity. So I'm not going to go in depth on this chart because, again, this is a review. There's going to be a lot of stuff I'm going to talk to you guys about today that is a review, okay? That I'm hoping you didn't forget how to do those things. And as I'm going through, the light bulb goes off and you're like, oh, ooh, I remember how to do this. But if that light bulb never goes off, what do you think you should do? There's two things that you could do. One is tutorials, and the second is what you think. Asking questions, I guess there's a third thing. Go back to your prior notes. Okay? Because I always tell my kids chemistry, it builds off of itself. I'm going to be talking about stuff from Unit 4, Unit 5, Unit 8, Unit 2 even. Okay? Hopefully we didn't forget those things. So the main gist of today is solutions. So in this unit, we're going to be getting way more in depth on homogeneous mixtures. Homogeneous meaning it's the same throughout. Okay, it's the same throughout. It is important to remember that solutions only contain very small particles that are dissolved in another substance. There are 3 important vocab words. This unit, heavy vocab. You're going to look at some solubility curves and have to answer questions, and then you're going to do math. So it's very similar to last unit. There are 3 things that make up or are components of a solution. Who remembers what the word is called if something is capable of being dissolved? Soluble, very good. Soluble. So when something is soluble, again, that means you're able to dissolve it. When you have something that is able to be dissolved, you have something that does the dissolving, and then you have something that is being dissolved. Okay? Those 2 words are solvent and solute. So the solvent, okay, is the dissolving medium in a solution. So that is what is doing the dissolving. Okay? So that is what is doing the dissolving. If liquid water is involved, which I would say majority of the time it is, but not all the time, and we'll talk about that. But if liquid water is ever involved, it will typically be the solvent. Water is known as the universal solvent, and we'll come back to that later. So if the solvent is what is doing the dissolving, your solute is the substance that is actually being dissolved in the solution. So we can look at salt water, because I'm sure everybody's familiar with salt water. So in salt water, what do we think the solvent is? Water. Which would mean the solute is what? Salt. Okay? The solute is what is being dissolved. Salt is being dissolved in water. Alright? Now, do solutions always have to be a solid dissolved in a liquid? No. Okay? We can have many different types of solutions. Okay? Gas, liquid, gas, liquid, liquid, solid, solid. So gas, liquid. It's probably the most common one, hopefully you guys can think of. What do you think is an example of a gas, liquid solution? What? Somebody said it. Soda. Right? Soda. So in soda, what do you think my solvent is? You have to be specific. Water. So if your parents are ever like, oh no, you can't have soda, that's not healthy, be like, it's water. Oh, kidding, okay. But it is, right? So what do we think the solute is? What is our gas in that? Carbon dioxide. Okay? So the water is dissolving the carbon dioxide, which is what is creating your carbonated drink. Okay? Now, obviously, there are other components in soda, but that's your solvent. You have one solvent when you have one solute. Okay? Gas, gas. What's an example of a gas-gas solution? Give you a hint. It's all around us right now. Air. Air. Does anybody know the main solvent in air? Very good. What are some of the solutes? Oxygen. What else? What? It's pretty small. Carbon dioxide. We're just going to do the main big ones. Argon is in there. And then tons of other little small ones. But the main ones are your solutes are oxygen, carbon dioxide, argon. Okay? But air. Gas, gas solution. What about a liquid, liquid? What? No, it's not a solution because they don't mix. Vinegar. Does anybody know the chemical name for vinegar? It's acetic acid. Very good. It's acetic acid. Okay, key word there. Acid, which means our solvent is what? Water, because acids are what? Aqueous solutions, which means they are dissolved in water. So our solute here is acetate. All right, last one, solid, solid. Can anybody think of a solid, solid solution? No. Say it again. Very good. What is that? What's an alloy? It's not just a metal. It's a mixture of metals. It's a mix of metals. So we can use 14 karat gold. If I have 14 karat gold, what is my solvent? Gold. Yeah. What do you think my solute is? Not copper. Silver. Okay. Questions about this first page? All right. I think the biggest misconception is, and it's okay to think this, but right off the bat when a lot of people hear solution, don't you immediately think of like a liquid? Right? But it's not always the case, right? I just showed you. You can have solid, solid, liquid, liquid, gas, liquid, okay? Solid, liquid, okay? So, does everything always dissolve in something else? No, right? It depends on if the substance is soluble or not. What is it called if something does not dissolve in something? Insoluble. Insoluble. Okay, when a substance does not dissolve in a solvent. Okay? Now for liquids, we have special names that refer to the solubility and insolubility. Okay, so this is for liquids. Okay? When you have a liquids that are soluble with each other, vinegar and water, they are miscible. Miscible. That's an I, by the way. M-I-S-C-I-B-L-E. What do you think it's called when you have liquids that are insoluble with each other? Immiscible. That's an E at the end. So, probably the more common example, oil and water. Everybody knows that oil and water do not mix, right?
Yes.
Okay, they never will. So, if we're looking at oil and water, because those do not mix, they rather separate into layers. Who can tell me what determines which liquid will be on top of each other? Olivia. Density. Density. All right. So we are now going to be getting into basically 3 big topics on determining the solubility of, this first one is covalent solutes and covalent solvents, but we're going to be talking about later on polar covalent solutes and polar covalent solvents. Then we're going to be talking about the solubility of ionic solutes in covalent solvents. And then illustrating the dissolving of ionic solutes in polar covalent solvents. So it is very important, okay? And at the end of our notes, we're going to do a quick summary, but it's very important that you are first able to identify if something is covalent, ionic, polar, nonpolar, all of those things, which we did back in Unit 4. What is covalent? How is something covalent? Sharing electrons, okay. Who shares electrons? What?
Two
Here, just sit right there. Sorry. 2 what?
non-solids.
No. 2 non-metals. I am concerned at the fact that no one right off the bat got that. My on-level kids can tell me what a covalent compound is. 2 non-metals. 2 non-metals. Thank you. You just have to sit at that lap table over there. Sorry. Yeah, where those 2 ladies are. All right. So, when we have molecular covalent compounds, and Jyoti, you'll need to grab the notes. When you have molecular covalent compounds, we have a rule that is like dissolves like. Like dissolves like. What does that mean? Like dissolves like. What? Raise your hand. I can't. Y'all, there's like 50 people in here. Yes. Okay, covalent dissolves covalent, but be more specific because it's not just covalent dissolves covalent. Polar dissolves polar. Non-polar covalent dissolve non-polar covalent. Like dissolves like. I can't say polar dissolves non-polar. Is that the same? Absolutely not. So that's where you get this. Polar and non-polar, they do not mix because like dissolves like. All right, who remembers this table? This table has been in your notes before. Nobody, one person remembers it. 2 people. Okay. Well, if you've forgotten about it, I need you to rethink about it, okay? Because what we're going to be doing here, when we're talking about the solubility of covalent solutes in covalent solvents, you have to be able to determine if something's polar or nonpolar. You can't just look at it on your piece of paper and go, oh, yep, that's polar. The only one you can know for that for is water, because water is a universal solvent. It's polar. Fun fact. Okay. But I put NH4, NH3, CCl4. You're not going to know unless you draw a Lewis dot, which is what we're about to do. Okay? So I hope you did not forget how to draw a Lewis dot, which a lot of people in first period did. So for this first example, I'm going to show you just a quick, easy step-by-step if you forgot, but just moving forward, I will not be doing that. And if you need refreshers, you have a couple of options that we went over earlier. 1, tutorials. 2. Look back in your notes. Okay? All right, so these are our steps. We're going to draw a Lewis dot for the compound. We're going to determine if the molecule is polar or nonpolar. We're going to then review what the following dominant IMF would be for that compound. And then we're going to figure out if the following dissolution will occur, meaning, will this dissolve? Okay? So, we have water, H2O. So, how many valence electrons does hydrogen have? 1, but I have 2 of them, so that means I have 2. How many valence electrons does oxygen have? 6. So really quick, right off the bat, if you already don't know that, tells me that you need to review. Okay, that tells me that you need to review. So in total, we have 8. So, what's my central atom here? Oxygen. Okay, so we're going to have hydrogen bonded off. I've used up 4 electrons, which leaves me with 4 more. Where do I put those 4? Why do I put them on oxygen? Because one, hydrogen only needs 2, but also, is oxygen happy? No, oxygen needs how many? 8. Now, looking at this, is this polar or non-polar? Why is it polar?
Because there's extra.
So hold on. Yeah? What'd you? No.
There's extra dots that are not connected to anyone.
Unshared electrons. That's what I want to hear. Well, 1, I did tell you that water is always polar. But 2, that's not always going to be the case. Like for all the other ones that we're about to do. But the unshared electrons. What do these unshared electrons do? What?
Make it unbalanced.
The electronegativity.
Yeah,
remember the pool of electrons. That's why hydrogen is pushed down. It's because of those unshared electron pairs, right? So this is polar. And what IMF is this? Hydrogen bonding. Why is it hydrogen bonding? When hydrogen bonds to either fluorine, oxygen, or nitrogen, remember H is Fon? I saw somebody do it. Yep, Fon. If hydrogen is bonded to fluorine, oxygen, or nitrogen, it's hydrogen bonding. Okay? All right. Phosphorus tribromide, Br3. How many valence electrons does phosphorus have? 5. And I just have 1 of them, so 5. How many valence electrons does bromine have? 7, and I have 3, so 7 times 3 is what? 21. So in total, I have 26. All right. What's my central atom? Phosphorus. All right, I just used 6 electrons, which leaves me with how many? 20. How many have I used now? I've used 24, so how many do I have left? So where do those 2 go? On phosphorus. Is this polar or non-polar? Why is it polar? Because there's unshared things on the thing. Unequal forces. This is what I'm talking about right here. Okay? I'm loving these words. Thank you. Okay? Because we're about to get into, when we're talking about partial positive, partial negative, we're going to start talking about electronegativity. And that's what we're talking about. Does bromine have a higher electronegativity than phosphorus? 100%. Because what's the most electronegative element we have? Fluorine. Look at that. Is fluorine... I mean, fluorine and phosphorus are pretty close, but fluorine and bromine at least are in the same group, right? So this is unequal, right? Because you got your bromines going out, and then you got phosphorus just by itself. Okay? Also, not to mention, we also talked about things being symmetrical versus unsymmetrical. What is the IMF here? Dipole, dipole. So the last question that this asks is, indicate whether dissolution happens. Will these dissolve with each other? So this is soluble. Why was this soluble? Just real quick, why was this soluble? Yeah, we'll go with that. Sounded like a mix of things. I didn't really hear people. All right. Questions about A before we move on to B? Yes, Maya. Yep. So you should have them somewhat pushed down a little bit because you have that unshared electron pair that is adding force. Just like here, I didn't have these next to each other because that would be linear, and H2O is bent, right? So it goes back to those Vesper shapes. Yeah. Good question. All right. We have liquid ammonia, NH3, with liquid bromine. All right, so, again, like I told you, I'm not going to be doing this anymore with you because that's from, like, forevers ago. How many total electrons do I have for NH3? 8. What's my central atom? Nitrogen. And I'm going to have hydrogen bonded off, which leaves me with 2 electrons left. Where do those 2 electrons go? On top of nitrogen. Alina, is this polar, nonpolar, ionic? What is it? What? No, it's not ionic. These are 2 nonmetals. I'm asking Alina. It is polar. I threw in the ionic as a little teaser. Okay. Yusuf, what IMF is this? Why is it hydrogen bonding? Because there's hydrogen with Fawn, right? Very good. All right, liquid bromine. Vineeth, how would I do my LDS for liquid bromine? What's that word? Diatomic. So it'd be Br2. Very good. So, very good. So I have Br bonded to Br, right? And then I add my other electrons. Okay. Rashiv, polar, nonpolar, ionic. Who else thinks it's polar? Who thinks it's ionic? Who thinks it's nonpolar? Who didn't raise their hand? Everybody else. Okay. My people who said it's nonpolar, why are you saying it's nonpolar? I agree, but why is it nonpolar? Are these the same element? So is the pool of electrons the exact same? And if I were to split this down the middle, is it symmetrical? 100%, right? So this is nonpolar. And what IMF is this? London dispersion. So, would this dissolve in each other? So what would we call this? Insoluble. So here's a little thinking question. If we know that water is polar, and we know that water and oil don't mix, then what is oil? Non-polar. Okay. Just wondering. I don't know. I don't know anything. So. All right. I would like for you to do C on your own. Okay. On nitrogen trifluoride, what did we say it was? Polar or non-polar? Polar. And what IMF? Okay. Now, I saw a lot of you guys struggling on liquid methanol, okay? You technically, so you have one central atom here. What's your central atom? Carbon. And branched off of carbon, you have 3 hydrogens and an oxygen. But you know, and you can figure that out based off of how the compound is actually written. CH3, that's telling you that there's hydrogen bonded to carbon. Well, if hydrogen's bonded to carbon, then that fulfills its 2 valence electrons, which means I can't have anything bonded off of hydrogen again. Oxygen is going to be bonded off of carbon and have its 2 pairs. This is not symmetrical at all. There's also various pools of electronegativity, which makes this polar, and it's hydrogen bonding because hydrogen is bonded to oxygen. So this would make it soluble. Questions? Uh-huh.
Does the oxygen get the electrons?
Well, I can't put them on carbon because carbon only can have 8. And I can't put them anywhere else because hydrogen only needs 2. And if I don't have them on oxygen, then oxygen is not stable. Yeah.
Why is it hydrogen bonded?
Because hydrogen is bonded to oxygen.
But it's also bonded to carbon, but it's not bond. Don't you have multiple different bonds?
You can have, yeah, multiple, like, IMFs, but these questions, I'm asking you for the dominant IMF. And hydrogen bonding, in this case, is more dominant than any other.
But isn't it like there's 3 bonds with hydrogen and carbon, but only like 1 with
Hydrogen bonding is present. Do you agree with that or not?
yes?
Then that's all you need to know. It's the dominant IMF. What other IMF would you say is more dominant than hydrogen bonding? Exactly, right? So that's,
Ion.
well, only ionic, but this is not ionic at all.
Yeah, opposite.
Yeah, yes.
On the
Hey, y'all, we can't have side conversations.
on the test, do we need to like write how we got however many electrons we have, like how we got to it?
I don't care about that.
Thank you.
Boys, do you have questions? Okay, then why are we talking? Okay. All right. I would like for you for D and E, if you don't know what you're doing or you want extra practice or help, save D or E for when you come to tutorials. That's perfect, okay? Save those. If you're like, I need help, me and you, or Tillman and you, we can work through those, okay? All right. We are now moving on to the dissolving of polar covalent solutes in polar covalent solvents. So, 4 covalent compounds dissolving in each other, IMF attraction, will be broken between molecules of the original substances. They then reform partial positive and partially negative ends of polar molecules of new substances. Have we talked about partial positive and partial negative before?
Yes.
Yes, we have. When we talked about that earlier, what were some ways that we determined what was partial positive and what was partial negative? Electronegativity. Now, do I require you to have the electronegativity values memorized? No. Okay. But I've told you, and at the time Ms. Apoko told you, if I don't give you the electronegativity values, how else can you figure out what is more electronegative or not? Periodic table. And what are you looking at on your periodic table? How close you are to what? Fluorine. Because what is so special about fluorine? It's the highest electronegative element we have. Now, I'm going to put this in parentheses just so you don't forget. There are electronegativity values on page 7. So if you flip to page 7, for reference, here are some electronegativity values. Okay? So just FYI. Now, again, I could not give you those values, but ask you what I'm about to ask you below, and you should be able to do it. Okay? Now, I'm never going to give you one that is like oxygen and chlorine, because is the difference pretty much the same on your periodic table?
Yes.
But are the values the same looking here? No. Who's more electronegative? Okay, so just FYI, okay? Again, our goal in life is to not trick you on questions. We want you to understand the content. So if I'm looking here, this is water, H2O. So why do we think oxygen is my slightly negative end? Higher electronegativity. Okay, higher electronegativity value. When I have a higher electronegativity value, my pull to gain electrons is higher. My pull to gain electrons is higher. Can anybody remember or tell me, do my noble gases have electronegativity values? Why? They're full. Do they want to pull any electrons? No, why would they? They're happy. They're noble. They got all 8. Okay? So, this is going to become very important because do opposites attract? Do like charges repel? Yes. So, I want something that's partial positive to attract something that's partial what? If I have two things that are partial positive, what's going to happen? Okay, it's just like if you put the battery in the wrong way, is it going to work? No. All right, so let's do this next example. So it asks us to illustrate the interaction between phosphorus tribromide, which we drew on the previous page, and water. It says to be sure to show the attraction between the different poles of the molecules. And then finally, it says to draw at least 2 of each type of this molecule, meaning I should have phosphorus tribromide drawn twice and water drawn twice. So I will show you what that looks like in a second. So first I'm going to draw phosphorus tribromide. And again, oops, should have given myself more room. We've already drawn this, so it should be familiar. All right. When I am deciding what is more electronegative or not, again, I have 2 things I can look at. I can look at my values, or I can look at my periodic table. What is the electronegativity value of phosphorus? Dang, girl, you dropping everything. 2.1. What about for bromine? 2.8. So, what is my partial positive element? Phosphorus. What is my partial negative? Bromine. Does it matter which bromine's partial negative? No, because do they all have the same electronegativity? Are they all going to have the same exact pool of electrons? Okay. Now, this is where the next part becomes. It's asking us to show the attraction. So, I can look up here because I have water up here. When I show my attraction, okay, if my bromine is my partial negative, what side of my of my water needs to be attracted to my bromine? Why hydrogen? Because it's partial positive. Thanks. You'll just go back with Ms. Ayers to get the notes, and then you'll just find a seat. So I'm going to draw my hydrogen. And I need to have oxygen, obviously, away from it. And I label this. This is my partial positive, partial negative. Is everybody with me right now on that? Now, I'm not done here because the question asks for me to draw at least 2 of each type of molecule. So now, what I'm going to do is I'm going to show my attraction From oxygen to what now? What is oxygen going to be attracted to? Phosphorus. Phosphorus is my partial positive. Bromine is my partial negative. Is everybody catching on so far? Am I done?
No.
What do I have to have one more of?
Water.
Water. So this bromine is going to be attracted to what? Hydrogen. And again, if you notice, on every single molecule that I drew, did I have something labeled partial positive, partial negative?
Yes.
And I'm letting you know right now, so nobody can say I didn't, and you can't get upset on your test when I take off for it. If you don't show for every molecule, both partial positive, both partial negative, you will lose points. If you do not show these lines, and you decide to go rogue and maybe do an arrow, and I'm going to be like, who taught you that? That is wrong. This shows attraction. Okay, it's the same way you'll see attraction when you get to AP, if that's where you go. Okay? Yes, Maya?
Does it matter which bromine or which hydrogen connect to
Nope. So, if you notice, my first bromine, I connected it to the one on the right, but over here it was my one on my left. Because they all have the same exact pool.
Also, does it have to go like up and like?
Say it again?
Does it have to go like up and like down like that, like the path? So it's kind of like going down.
I mean, I just did that based off of the way that these are drawn. You're not going to probably have to where it's in a straight line. It's kind of odd that way. But it's showing this because anytime I have my attraction, whatever is my partial positive, and like that's why these are attracted. So these should be pointed away. Like I shouldn't have something over here. Does that make sense? Yeah.
How do you go from positive to negative first? You always have to go.
Say it again?
Why didn't you go like make the negative to positive first? It doesn't matter which one you start with.
You could do the other way around.
Like if I drew like water first?
No, I mean like if you went phosphorus to oxygen first. Does that matter?
Well, phosphorus is my partial positive.
If you were to have phosphorus and oxygen.
Oh, okay, I get what you're saying. I mean, it's fine. It just depends. As long as your partial positive and your partial negative are together, then that's fine. Yeah. Okay. Any questions? Going once? Going twice? Okay. All right. This next page really should be a full review. It's determining the solubility of ionic solutes in covalent solvents. So, for ionic compounds, the rules aren't quite so clear. The ability to dissolve depends on the relative strength of the solute-solvent interaction. So first, ionic compounds will only dissolve only in polar covalent solvents. They do not dissolve in nonpolar covalent substances. Okay? Putting stars because that's important. Even still, there are certain ionic compounds that will dissolve in polar substances and some that will not. There are special rules for ionic substances in polar covalent solvents like water. Have you seen this before? Do you have to have this memorized?
No.
So I give this to you on your test?
Yes.
Okay, just want to make sure. Now, my kids know that this is a table. If you don't know how to use it, It becomes a resource the moment you actually know how to use it, right? So you need to make sure you know how to use it, okay? With our solubility rules, if a compound is soluble, what is the state that we write? AQ, very good. AQ. Remember whenever you're doing that on Unit 8, types of reactions? No? Okay. If a compound is insoluble, that means that it will not dissolve in water, and it will form a what? Well, what? Precipitate. I heard some of you guys say it. That substance, you will get a S designation, okay? A special note about water, and I talked about this earlier. Because so many substances are either polar covalent or an ionic compound soluble in water, because again, like I told you, water is polar, it dissolves so many substances. Whenever you have a lab and we need to make copper sulfate, copper 2 sulfate comes in, it's like a really pretty turquoise powder. And we take distilled water, because that is what we will do, is we will take copper 2 sulfate and dissolve it in water. That's how we make our solutions, okay? Because we know that it dissolves. I know that if I take this binder clip and put it in water, is it going to dissolve? No, so it would be insoluble, right? Water is, like I said earlier, it's known as our universal solvent. Universal solvent, because it dissolves majority of our stuff, okay? All right, I'm going to do this first one with you, and then I'm going to have you do the rest of them. So it says, for each of the following, use the solubility rules to determine if it is soluble, if it's a soluble polar covalent solvent or not. Put the correct state symbol next to the compound. NaCl. Is this aqueous or solid? All right, I want you to do the rest of them. Before I show you the key, I'm going to just call in some people to tell me what it is. You just need to say aqueous or solid. All right, AGBR Amelia. Say it again. Solid. NH4NO3 Joel. Okay. Zara CAF2. Okay. MGO Shishi. Okay. Caroline, CaOH3 or OH2. Which one is it? Aqueous. Gabe, MgCO3. And last one, Misha, CaSO4. Very good. Any questions on those? Any questions? Yeah.
So that just means we're just trying to find if they're soluble in water, right?
Yes.
Like, and polar covalent.
Yes. Mm-hmm. Yep. All right. Last little part of today's illustrating the dissolving of ionic solutes in polar covalent solvents. Okay, so understanding, this is a big thing. Dissolving, and this new word I'm about to talk to you about, dissociation. Let me write it down first. Dissolving and dissociation are very different, okay? So dissociation is the process of a compound separating into its ions when dissolved in a polar solvent in a reversible manner. Okay? Acids, bases, and ionic compounds can all undergo dissociation. Somebody tell me why you think that is. What do acids, bases, and ionic compounds all have in common? They're what? Well, H2O is multiple elements. So what is different about acids, bases, and ionic compounds? They have a charge. If something has a charge, that means it's a ion. Keyword ionic, right? Can something dissociate into its ions if it doesn't have ions? So when I said earlier, I said dissociation and dissolving are different. Does sugar dissolve in water? Yeah, sugar dissolves in water. When sugar dissolves in water, does it dissociate into ions? Why not? Why does sugar not dissociate into ions? It's covalent. And earlier, I think you actually said it earlier, covalent, you share electrons, right? You're not transferring, trying to get your charges evened out, right? Sugar dissolves in water, but that does not mean that it dissociates in water. You've got to know that, right? There's lots of things that can dissolve, okay? But some of those things don't always have charges. And the reason why I'm really emphasizing those things is, I don't know if it's next class or the class after, we're going to be talking about electrolytes, okay? And in order for something to be an electrolyte, it has to have charged ions. Well, sugar is not going to have any charged ions, okay? All right. So again, dissociation. It happens when the ionic charge bond between ion is weakened due to the formation of new IMFs. That new IMF formed is called ion dipole IMF. So, while polar covalent compounds may be soluble in water, they do not dissociate, again, because they are not composed of ions. That's what I just talked about. So, when we illustrate the dissolving process for ionic solutes in covalent solvents like water, we have to show the positive and negative ions separated with water surrounding the ions. The water molecule will position themselves in such a way that positive and negative charges will attract. So you can kind of see that right here. Okay. So, who can remind me when we have something that is ionic and it, dissociates, how do I draw the LDS? What do we have to have for ionic? Brackets and charges. So this asks us for KBr, and also, side note, okay, sidebar. In your notes right here, I say for potassium bromide, and then I put in parentheses KBr. On your test, I will not tell you what the formula is. And based off some of y'all's retests, you guys don't even know what methane is. CH4, by the way. Which is concerning. Okay? Also, fun fact, not one, not two, 6 people, and I'm not dogging on Miss Apogo's class, but none of my students did it. What is the phase change when you go from a gas to a solid? Deposition. You know how many people wrote decomposition? I'm sorry. What? Decomposition is not a phase change. It's a type of reaction. Just wanted to put that out there. It was really bothering me. If only one person did it, I'd be like, okay, maybe they just miswrote. But 6 people? Like, good God. It's embarrassing. Did have me laugh a little bit. And then I put an X and said -1. Okay. So I'm going to put that out there. KBr. This first part that I'm going to do is just pre-work for the actual work, but it's important. So when I break this up, let's stop for a second. When I break this up, and I have my brackets, okay? Remember, in ionic, we transfer electrons, right? Potassium has 1 electron, 1 valence electron. Bromine has 7. So who's going to transfer what? Potassium's going to transfer its electron to bromine. Does that mean potassium has 0? No. How many does potassium have then once it transfers? 8, right? But do we show those 8? No. So when I write this, I have potassium in its bracket. And then I have bromine with its full shell. Okay? Again, this right here is the pre-work that I'm just showing you. This is going to be in H2O, and we know. Okay? I have this. We know that oxygen is my partial negative. Hydrogen is my partial positive. So, this is, again, just pre-work for you to kind of see. So when I come over here, I have my potassium, okay? And it tells me to show at least 3 water around each of my cation and anion. Is this my cation or my anion? This is my cation because it's positive. So when I show my 3 waters around my cation, how should the water be written? What should be closest beneath to my potassium? Why oxygen? It's partial negative, right? So, it's going to look like this. Did everybody see that? Now, some of you might be thinking, like, what if I just put them, like, all bunched together? Please don't do that. Why do you think it's important to have them spaced out? What? Not so much neatness.
What else is that?
Equal force, too, right? Equal force. So that was my cation. Now when I show my anion, what is going to be closest to it? The hydrogens. Now obviously I would have put this one more center, but I ran out of room. Yeah. Say it again. In this example, I don't specifically ask you to include the partial positive and negative, but if on your test I asked you to include the partial positive and partial negative, yes, you would have to include it. It's a great question. Yeah. Yeah, like I always tell you, like, show at least 3 waters, yeah. Just like on this example I said to draw at least 2 of each type. Yeah, I will tell you that, 100%. Yeah. So, is this partial, like this is your, obviously your partial negative, so then I would have my partial positives here. Right? Because this is my partial negative. Okay. Other questions? Alright, one more, yes. What? It's the symbol that we've been using? Up here, it's S. It's what we did right here. Yes. We did this in like Unit 4. Welcome. Alright. Last thing, I'm going to do a quick little summary, okay, of the solubility rules and illustrations. Okay, this is big. My first period, they said that this was helpful to kind of like wrap up what I just taught you today, because it was overload, right? Like, trust me. Like, come my 3B tomorrow, I'm going to be like, oh my god, I don't even want to draw another Lewis dot structure, okay? So to summarize our solubility rules, covalent and covalent. What is the saying I told you to remember? Like dissolves like. Now this like dissolves like, that comes from what? Depending on the what? Polarity. Yep, polar, nonpolar. So polarity. Okay. When I have my covalent plus covalent, what do I have to draw? Draw a Lewis dot. Draw LDS, Lewis dot structure. For covalent and covalent, is there dissociation?
No.
No! Why? Very good. And then what attract each other? What is it called? Blank attracts. No? Well, yeah, but it starts with a P. Like more chemistry terms. The poles. Very good. Poles attract. When it says poles attract, it's talking about partial negative poles attract partial positive poles, right? Okay. Now, summarizing, covalent plus ionic, nonpolar plus ionic. Soluble? Question mark? Some people are shaking their heads. Some of y'all are looking at me like deer in headlights. What? No. Correct. Never soluble. Nonpolar plus ionic. Never soluble. That's it for that one. Last one, polar plus... Yes, Liam.
Right, so if they give you your covalent, you have to draw your LDS to figure out
Mhm.
the polar.
Yep. 100%. Because, I mean, if I give you CH4OOH, you're going to know right off the bat if that's polar or nonpolar?
It will be polar because I can't like put that around.
Yeah, you could. You'd have to draw it out to figure it out. Yeah, 100%. You have to draw your LDS to figure it out. 100%. Okay? Last one, polar plus ionic. What do we always have to check for polar plus ionic? What do we always have to check? No? Very good. Check the solubility chart. Now, I heard two people say dissociation. So, yes, dissociation does occur. Because dissociation is the splitting into ions. And then finally, what surrounds our ions? Water, very good. And why is it that water surrounds our ions? Because, that's what it's dissociated into, right? Is into water. So, this is a really helpful little tool to remember whenever you're answering these questions and when you're doing your practice worksheet for homework, page 1 through 3 today, BTW. On